So hydration has become -10, but lattice has become just -20. So hydration has suffered a large change, but lattice has suffered a small change. All right. Okay. So what is the solution enthalpy here? Solution enthalpy here is -30. And what is the solution enthalpy here? Solution enthalpy here is +10. Okay. So solution enthalpy has become positive, or solution enthalpy has increased. And if you do remember from the graph that if solution enthalpy increases, then solubility decreases. Okay. So down the group, the solubility of the sulfates would decrease. Now what about in case of small ions like hydroxides, fluorides, etc., etc.? Okay, so hydroxide has got a very small size. So it has a very high charge density. So it would result a very strong attractive force with the water molecules. Okay, that means due to the presence of smaller ions like hydroxides or fluorides, the attractive force would be very large. Okay, the attractive force would be very large. So the hydration energy would also be very high. Okay, so hydration energy has got a very high value if hydroxides or fluorides, which are smaller ions, if they are present, because they have a small charge density and they would attract water molecules very strongly, because force of attraction is directly proportional to charge density. I am repeating the same things again and again. Okay, so now the thing is that okay, so hydration of hydroxides and fluorides, they have a very large value. So if there is any change in the hydration down the group, that would be a minor change or a very small change. But now comparatively, it would seem that lattice changes more than hydration. Okay, let me tell you about the solubilities of magnesium hydroxide and, for example, barium hydroxide. All right. Okay. Look, for instance, think that lattice energy, the overall hydration of the magnesium and the hydroxide ion altogether is -60. No, it's more. It's -6,000. Okay, and the lattice energy is -60. Okay. Okay. Here, in case of barium hydroxide, consider that overall hydration energy is -5,980, and the lattice energy is -40. Okay, look, so now tell me, no, wait, 990, and it's -40. It's just like a change of 20. Okay, as before in case of sulfates. Okay. So look here, what is the value of solution enthalpy? Tell me. The value of solution enthalpy is minus 5940. Okay, if I'm not wrong. Tell me the value in this case. Here the value is minus 5950, isn't it? Okay, now look, very important. Look, here it is minus 5940, here it is minus 5950. So the solution enthalpy has become more negative, isn't it? So you might think that hydration energy is lattice energy in this case is decreasing more. Yes, you can think in that way, but I will tell you that preferably don't think like that. You might think it in this way, that in case of large ions like sulfate, the hydration energy was decreasing to a large extent compared to lattice. Okay, like just rewind the video and look at the sulfate. But in this case, the hydration energy is changing to a very small extent, or the percentage change is very small. Okay, so the hydration energy is changing very less, because the negative ion, the hydroxide, it has got a large hydration energy already, because it has a smaller size, higher charge density, and higher attraction with the water molecules, so higher hydration. So hydration is already higher, so any change in hydration would be a very small, would affect the enthalpy, or would affect the hydration enthalpy to a very small extent. So there is a very small change in hydration, but in comparison the change in lattice is greater. Okay, so what's happening is that when in case of hydroxides or fluorides, the change in hydration is very small, and in comparison the change in lattice would be larger. So what happens? The solution enthalpy down the group becomes more negative, that means decreases. So solution enthalpy becomes more negative and the solubility would increase. This will be the case in case of magnesium, in case of both hydroxide salts and fluoride salts. Now can you guess that what would happen in case of nitrates? If I tell you like magnesium no, not nitrate. If I tell you in case of chlorides, magnesium chloride and barium chloride, which would be more soluble? Indeed, magnesium chloride would be more soluble and barium would be less soluble, because chlorine is large, its mass is greater than 20, so it's a large anion, large negative ion, so its charge density would be lower, so the force of attraction of chloride with the water molecule would be less, so hydration energy would be less. So any change in hydration energy of these positive metal ions would drastically affect the overall hydration energy. So down the group, lattice energy would decrease, but hydration energy would decrease more, because the negative ions already have a lower hydration energy. Okay, so when you are predicting solubility of salts down the group, just think about hydration, that is the hydration decreasing to a large extent, or hydration decreasing to a very, very small extent. And to get that prediction, just look at the negative ion. It's a shortcut. Okay, all right. So down the group, the solubility of sulfates, nitrates, the large anions would decrease, and the solubility of salts which contain small anions like fluorides or hydroxides, they would increase. Okay, now we are at the last part of our study. It's sorry, the polarization is still left. Okay, I guess that I'm taking like a crash course class, because I'm finishing the whole chapter in a single video. I'm sorry if I'm giving a lot of pain, but I want you to finish the syllabus earlier. Okay. Now, look, for example, carbonate. Tell me about magnesium carbonate and barium carbonate. Okay. Which ion has got a larger size? Obviously, barium has got a very large size. So the charge density of barium is less. So its power of attraction or power of attracting the carbonate ion would also be less. But magnesium is very small in size, so its charge density is high. So its power of attraction or power of attracting the carbonate ion would also be high. Okay. So this it is possible that this magnesium ion that is due to attraction of the magnesium ion, the shape of the carbonate ion would get distorted. Okay, the shape of the carbonate ion would get distorted and would be very easily broken down by heat. So magnesium carbonate is less thermally stable, but barium carbonate is more thermally stable, because in case of barium carbonate, the ions, the carbonate ion is not polarized, because barium has got a lower charge density, so it would not cause a very great attraction on the carbonate ion, and the shape of the carbonate ion is not distorted, so the bonds remain strong. Okay, let me go back to this slide. So the bonds remain strong like this case, and so this ion is not easily broken. Okay, so as you go down the group, the shape and the size of the positive ions increases, so the charge density decreases, so they cannot attract the negative ions so strongly, so the negative ions or the bonds in the negative ions are not polarized or not deformed, so they become more thermally stable down the group, isn't it? Like the case of I would suggest you to rewind the video and listen to it again about magnesium and barium. So that's all for the thermal stability. Now the last part of our chapter is the Born-Haber cycle, although this is the middle part of the book. Okay. So what is a Born-Haber cycle? A Born-Haber cycle is just a modified version of the Hess's law, and here we find what we do is that we find the formation enthalpy from all other enthalpies. Okay, and first of all, I would tell you to memorize this shortcut, that formation enthalpy will be equal to AIELA, AIELA. Okay, A stands for atomization, I stands for ionization enthalpy, A for atomization enthalpy, and I for ionization enthalpy, and E for electron affinity, and LA for lattice enthalpy. Okay, so AIELA. So formation enthalpy is the sum of AIELA. Okay. Now there is a formula that links bond energy to atomization enthalpy. So what is the formula? Please write it in your copy. It's not written in this lecture sheet. I'm writing it here. Enthalpy change of atomization must be equal to bond energy into number of bonds divided by number of atoms. Okay, so enthalpy change of atomization. Okay, I'm writing it over here again. Enthalpy change of atomization would be equal to bond energy of a bond into number of bonds divided by number of atoms. Okay. Like for example, look at the structure of P4. Okay. So, how many bonds you can possibly find here? You can find 1, 2, 3, 4, 5, 6, 6 bonds. Okay. So, what would be the enthalpy change of atomization of phosphorus? The enthalpy change of atomization of phosphorus would be del H is equal to bond energy of phosphorus into number of bonds, that means 6 bonds, and number of atoms, that means 4 atoms. Okay. So, this is how to find the atomization. Okay. Now, let us look at the Born-Haber cycle in the formation of aluminium oxide. Okay. Look, so AIELA, A for the atomization enthalpy, I for the ionization enthalpy, E for the electron affinity enthalpy, and La as the lattice energy. Okay. So, look here we have to form Al2O3. So, we are taking 2 aluminium and we have to take 3 oxygen. So, we are taking 1.5 O2. So, the first step is AIELA. A is the atomization. So, atomization means forming gaseous atoms. So, we are forming 2 gaseous atoms here and 3 gaseous oxygen here. Okay. So, look, so what we have to do is we have to multiply 2. We have to multiply 2 with the atomization of aluminium, since 2 atoms of aluminium is formed, and we have to multiply 3 with the atomization of oxygen, since 3 oxygen atoms are formed. Okay. So, how you will find the atomization of oxygen? First count how many atoms are formed here. Okay, 3 atoms are formed here. No, sorry. So, we have to find the atomization of oxygen. Okay. So, oxygen has got this structure OO double bond. So, del H atomization of oxygen will be equal to bond energy into how many bonds are here? There is 1 bond, and how many atoms are being formed? 2 atoms. Okay. So, this would give you the atomization of oxygen, and since you are forming 3 atoms of oxygen, so you have to multiply this value by 3. Okay. Okay, so we have done the atomization. Then AIELA, I means ionization, ionization means forming the positive ions. Okay. So, consider 1 aluminium. So, you are converting a neutral aluminium to +3 aluminium. Just remember that there has to be 3, it has to be a 3-step process. All right. So, first you have to convert Al so you have to convert from Al to Al plus, then Al plus to Al2 plus, then Al2 plus to Al3 plus. Okay. So, this is the first ionization energy, this is the second ionization energy, and this is the third ionization energy. All right. Okay. So, you have to go for 3 ionization energies, the first, the second, and the third, and you have to do it in case of 2 atoms. Okay. You have to do it in case of 2 atoms. So, you have to multiply the whole thing by 2. Okay. So, the first, the second, and the third ionization energy, they are all added together in forming Al3 plus from Al, and then it is multiplied by 2 because there are 2 atoms. Okay. So, AIELA, we have done A and we have done I. Now, we will go for E. E stands for electron affinity. So, we have to form O2 minus, right? We have to form O2 minus. So, that means from O we first have to form O minus, then from O minus we will form O2 minus. So, this is the first electron affinity and this is the second electron affinity. Okay. So, for one oxygen atom we have two electron affinities. So, we are adding the two electron affinities as Ea first, the electron affinity first, and Ea second, that means the electron affinity second. Okay. And then we are multiplying this whole value by 3 because 3 oxide ions has to be formed. So, we have got aluminium ion and we have got oxide ion. Now, these gaseous ions will be combined together to form the solid aluminium oxide. And when gaseous, just remember that gaseous ions are combined to form a solid, we call it the lattice enthalpy. Okay. Okay, and what is the formation? If you do remember from your AS level, formation means 1 mole of a compound is formed from its elements. Okay. So, from here to here we would call it the formation. Okay. Now, it is so simple that we have got the A, we have got I, we have got E, we have got I, and these all would have to be added together to get the del H formation, and this is how the Born-Haber cycle works. Okay. Okay. So, A, I, E, L, I, to get the formation. Okay. So, that is all for today, guys. I will send you I will make, or I will prepare a question answer session for this whole chapter, but before going into that video, first make sure that you have understood the whole of this chapter, you have made a note and you have gone through the book. The book is for this chapter, the book is very important, and please inform me or tell me your problems by commenting below this video, or sorry, not in this video, by commenting in the group of Science Academy that you are added. I will give video solving there. All right, no problem. Okay, guys, so that's all for today. We will see you in the next class, and I will be starting electrochemistry. Thank you. Bye.